So yeah, I'm going to talk about many nodal domains in random regular graphs, and this is joint work with Shrishenu Ganguly, Siddhant Mohanty, and Nikhil Srivastava. And Siddhant actually did his undergrad here. So funny coincidence. Okay, so what we're going to be talking about is graphs and then adjacency matrices of graphs. So for the adjacency matrix, what we do is that we take the graph, we have a matrix where rows and columns correspond to vertices, and then we put a 1 in an entry if the two vertices are connected by an edge. So this matrix is symmetric. The eigenvalues are real, and therefore they can be ordered. And during this talk, we'll also consider the combinatorial Laplacian, which is another matrix of the graph, which is D minus A, where D is the diagonal matrix of degrees. So when we think about graph partitioning, often we'll partition according to the entries of the eigenvector. And this is done when we think about sparsest cuts, ky sparsest cuts, maximum cut. An example of this is what are known as Fiedler cuts. So for a Fiedler cut, we take the second eigenvalue of the adjacency matrix, then we can order according to the value in that eigenvector. And then Fiedler cuts ask us to look at the different cuts that we have by partitioning according to the values in this eigenvector, right? So we just look at the series of cuts according to this value. Yeah. Yeah, exactly. So yeah, Fiedler cuts are just, yeah, exactly. If I sort them according to the entries of the eigenvector, and then the different partitions this induces are if I choose different levels of a different value at which I cut my eigenvector into two parts, my graph into two parts. So the y dimension is some arbitrary. Yeah, in this graph, yeah, it's arbitrary. Right now, I'm just thinking about cuts from left to right. Yeah. And yeah, once again, at any point, if you have questions, definitely just let me know. So, for example, like Fiedler cuts are something that can be used to prove Cheeger's inequality for graphs. Is that something that you're familiar with? So, what we're going to ask is these. Like we said, by partitioning according to the eigenvector, this will induce a partition of the graph. And what we want to do is we want to figure out more about what this partition actually gives us. So usually, these partitioning algorithms, or often I will say usually, are concerned with how many edges do we cut. But we're going to be asking other questions about this partition. Specifically, we're going to be looking at the connected components that we have when we do this partitioning according to the eigenvector. And these connected components are actually a well-studied object, and they're called nodal domains. So yes, the nodal domains are, if I'm given a vector f, I look at the maximum connected components of the same sign. So here's a graph. I can then partition the graph according to, and on each vertex, you can see that there's a number which corresponds to the value in the vector. I can then partition the graph according to whether it's positive on this vector or negative on this vector. And then the nodal domains will just be the maximally connected components after this partitioning. So just another simple example, and once again, just the maximally connected components. So you just remove the edges. Yes. Of the cut and then run the connected components out. Yeah. So the nodal domains are these components, yes. So it definitely should be noted that these are studied in continuous space as well as discrete space. So there's this well-known theorem of Richard Courant which says that if instead of the eigenvectors of a graph, I look at the Dirichlet eigenfunctions of some bounded region, that the kth eigenvector induces at most k nodal domains. So for example, this is the sixth eigenfunction of the square, and I made a heat map, and you can see clearly that there are 6 nodal domains when I've done this. Okay, so, but anyway, going back to discrete space, so graph nodal domains. There's a series of works on this. We mentioned Fiedler before. So Fiedler showed that if I take a tree graph, then the k smallest eigenvalue of the combinatorial Laplacian, that eigenvector has exactly k nodal domains. So exactly the number of nodal domains for every eigenvector of the Laplacian for a tree. So then later on in 2000, there was this result, which was a discrete version of Courant's nodal domain theorem, which says that for any graph, the kth eigenvector has at most k nodal domains. Then Dirk-Helayko generalized these results by saying that if I have a graph and I know that it's close to tree-like, so what you should just take away is that if I'm L edges away from being tree-like, and then a Schrodinger operator, that's just a generalization of the Laplacian, so you can just think about the Laplacian again, that the kth eigenvector now has between k minus L and k nodal domains. Yes?
So the first thing says that corresponding to the smallest eigenvalue, the eigenvector all have same sign.
Yeah. So if I just have if I have one nodal domain, that means that my eigenvectors are of the same sign. And if I look at the combinatorial Laplacian, the smallest eigenvalue is 0, which corresponds to the all ones vector, right? Which is all the same sign. So yeah, similarly, the second eigenvector will have 2 nodal domains, etc. Yes.
That second result, what would happen if the initial graph had k plus 1 connected components?
If it had, oh, fair enough. Yeah, I should add this should assume connected. Yeah, that's fair. Yeah. No, yeah, I should have put that in. Thanks.
Also, is it Courant?
Oh, what did I say?
Courant.
Oh, okay, sorry. So, okay, so anyway, we have a good idea of what happens when our graph is close to being tree-like. Right? Yes, question.
So the third one makes some assumption about sparsity of the graph.
Yes.
But the second one is not.
Is for arbitrary graphs, yeah.
I was trying to figure out how come the third one is generalizing the.
Because the upper bound that you get is k, right? So no matter what this L is, you still get an upper bound of k. Yeah. Yeah. No, thanks. Thanks for the question. Any other questions right now? Okay. So we have a good idea of what happens when our graph is close to being tree-like. So we can ask though, like, I have this upper bound of the number of nodal domains. Can I say anything more if I have a dense graph? And perhaps the most natural question is, what if I just select a graph at random? Okay, so yes.
Sorry, so I just have, there's still like like so for like for the tree, if I don't order like the the 5 plus first eigenvector always is more.
Yeah.
Is that also true in general?
Oh, that's a really good question. That's not always true. Yeah, that's not always true. For example, like the examples don't necessarily look like this, but one example is I could create some gadget, right, which is incredibly localized, and that will have, it could be of eigenvalue 0, which will be near the middle of the spectrum, but it could have 2 nodal domains, something like that, whereas like other surrounding eigenvectors will have many more nodal domains. Yeah. Okay, so the first model that you might think about, oh, sorry, question? Not always. Because of that example, also you'll see that even for Erdős-Rényi, that's not the case. Yeah. So the first random model that I'm going to talk about is the Erdős-Rényi random graph model, where I include each edge independently with some fixed probability p. So once again, there's a series of results about what nodal domains of these graphs look like. And yes, it actually shows that for graphs that look like this, there are far from k nodal domains for the kth eigenvector. So a result from about 10 years ago for Deckel, James Lee, and Nati Lineal show that for a GNP graph, if I fix p, then the eigenvector of the adjacency matrix, all eigenvectors of the adjacency matrix besides the first is just the trivial eigenvector, have all but a constant number of vertices are in two very large nodal domains. And then soon after this, there were new delocalization results that Aurora and Bhaskara used to show that, in fact, there are exactly two nodal domains for these dense GNP graphs. Then we know that we have exactly two nodal domains. Well, Mark Rudelson showed that every vertex in each of these nodal domains borders the opposite nodal domain. And then Han Huang and Mark Rudelson showed that kind of these two pair results, one for bulk eigenvectors, one for edge eigenvectors. So eigenvalues in the center of the spectrum versus eigenvalues at the edge of the spectrum. And they show that these two nodal domains are approximately the same size. So they're both of size about n/2. So we have this very set structure for Erdős-Rényi graphs. Okay, so what do I want you to take away? Yes. Sure.
So some of these things could be tested with experiments, right?
Yes.
And you could decide whether the bound is tight or very crude.
Uh-huh.
And like in the second result there, if n was 1 million, that would be probably using half of one.
Yeah.
I don't know. Does anybody ever do that, or is that not something that anybody does?
Doing tests on these?
Experiment, yeah.
Yeah. People will use experiments on these. Yeah, and I suppose I'll show some results of experiments later, but what you have for the Erdős-Rényi case is that you have this very set result, right? That you have exactly two nodal domains that are almost exactly the same size from one another for every eigenvector. Yeah.
The last one, you could say, try to test our approximation.
Great. Yeah. Any other questions? Okay. Okay, there are a couple of things that I want to take away from this series of results. First of all, as I mentioned, oftentimes these nodal domain results will follow from what are known as delocalization results, which is something that we'll do as well. So what is a delocalization result? Well, it will vary on which proof we're talking about, but some examples of this are in the first proof that I showed in Deckel, Lee, and Lineal, they used a recent result that said that if I have a rectangular matrix with independent Bernoulli entries, then the probability that any fixed vector is the image of a vector of norm 1 multiplied by this matrix is exponentially small. This is an example of a delocalization result. Another type is that Han Huang and Rurelson, they use a result of Bourgaud, Huang, and Yao, which said that eigenvectors of Erdős-Rényi graphs have Gaussian behavior. It's a loose way of talking about it. And this is something that they use fundamentally to prove their nodal domain results. Now, intuitively, what is going on here? What's going on is that Erdős-Rényi graphs are too dense to have more than 2 nodal domains. Basically, like any vertex will always be connected to some vertex of the same sign in such a way that it will eventually clump together and we'll get a very large nodal domain. So in the same paper from 10 years ago, Decollé and Lineal observed that according to simulations, if instead of looking at an Erdős-Rényi graph, I look at a randomly selected d-regular graph for small d, that the number of nodal domains increases with k. So we no longer have this behavior where I have exactly 2 nodal domains. I now have behavior where I have an increasing number of nodal domains, the higher the index of my eigenvalue is. So, and this is something I just ran a couple days ago, this is the number of nodal domains for 1000 vertex graph that's 3 regular generated at random. And this is, as opposed to before, you see that, and this is counts the number of nodal domains, is the y-axis. So for the first 200 or so eigenvectors, there's a constant number of nodal domains, probably around 2. But then at the edge of the spectrum, for the 1000th eigenvector, we get a very high number, almost 1,000, or almost 900 nodal domains. So our question is, can we prove this non-trivial structure of nodal domains for a randomly selected d-regular graph? So verify the simulations that Decollé and Lineal had in their original paper. Yes. Separation. Sure. I think if you knew, okay, so there are a series of results that talk about approximations of eigenvectors, and basically what you can do is you can say results about sums of eigenvectors within a given window, right? So if you knew that an eigenvector were actually distant from every other, an eigenvalue were distant from every other eigenvalue, then you could say more precise things about what that eigenvector looked like. But that being said, yeah, how to actually use that, it's not immediately sure. Yeah.
I'm confused about something like 20 slides ago.
Okay.
So I can count it over these nodal domains.
Yeah.
You take the k eigenvalue,
Yeah.
eigenvector,
Mm-hmm.
and then you run through and pick a cut value.
Sorry, it's
Cut value, and then you for each cut value, another nodal, and then you take the minimum, maximum. When you do that, then.
sorry, I should have made that more clear initially. So we're taking it just to be 0. So we're fixing the value to be 0. So we're just looking at the positive entries and the negative entries. So basically the Fiedler cut for value equals 0. Yeah.
So that's a Fiedler cut.
Well, a Fiedler cut being just like a partition of the entries according to the value of the eigenvector. But we just take, as opposed to minimizing over all possible values, we look at a specific value, that value being 0. Yes.
Yeah, so is there something about how different 0 make it so
That's a good question. Presumably, well, so yeah, assuming that you're renormalizing, right? I think you probably could. I think you could get epsilon away from 0 at least, which is the first step, just by using the Gaussian behavior of these random graphs, like Erdős-Rényi graphs. It'd be an interesting question in terms of like if I go any constant away. I feel like the answer is yes, but yeah, I'm not sure. Okay. Okay, so now we're looking at random regular graphs. So you can think about this just if I look at all graphs on n vertices that are deregular, and I just select one uniformly at random. And we denote this by G and D. So this is G23. It's 20 vertices, 3 regular. I did. Yeah, which might have been a waste of time, but I did it. Almost, yeah. Actually, yeah, I don't know if it is. So the other thing that it's worth mentioning is that there's motivation here from mathematical physics. So the trajectory of electrons in small spaces is predicted by what's known as quantum billiards, and loosely what we're talking about is if I do dynamical billiards replacing deterministic paths by movement in quantum waves. So Schnirelmann had this famous result from the 70s, which says that almost all high energy eigenfunctions of quantum billiards are equidistributed. So Berry then had a conjecture which says, not only do you have this, but the distribution should behave like a random wave, in the sense that statistics should behave like Gaussian random variables with this fixed covariance, which is based on the distance. This is just a Bessel function, but you should just think about it as the covariance is based on the distance and goes down as the distance gets larger. So one of the implications of the random wave conjecture would be that there are many nodal domains. So if eigenfunctions had many nodal domains, that would suggest Berry's conjecture. So that was all in continuous space. So once again, going back to discrete space, regular graphs have been used as a model for quantum chaos for at least 20 years, for more than 20 years. So for these graphs, instead of looking at the high energy limit, we look at the limit on the number of vertices and examine eigenvectors of the adjacency matrix. So an example of a result in this area is Anantha-Raman and Laplacian showed a statement that was analogous to Schnirelmann's theorem on the last slide for large regular graphs. So something that we want to do is show support for the discrete version of Berry's conjecture by showing that there are many nodal domains. Any questions? Oh, so Berry's conjecture is that yeah, so it's just saying that these eigenfunctions, like the distribution of values of the eigenfunctions behave like the distribution of Gaussians with this fixed covariance that depends on the Bessel function. Yes. Yeah. We'll talk about that. But yeah, whatever the discrete version would be, this would show that. All right. So it's now about halfway through the talk. So probably a good time to present the theorem that we actually show, right? So what we show is that we fix the degree of the graph and we fix some value alpha. Then with high probability, every eigenvector of the adjacency matrix of a random regular graph with sufficiently small eigenvalue has an almost linear number of nodal domains. Okay, so we have this condition right on the eigenvalue. So this is at the very bottom of the spectrum. Specifically, the number of eigenvalues that we're talking about here is approximately c times d to the minus 3/2 n eigenvalues, and that's just from looking at the Kessler-McKay measure. So you can see what I'm talking about. The number of eigenvalues for which our result holds. This is for a 3 regular graph. This tooth shape is the Kessler-McKay measure for 3 regular graph, which is the spectral measure of 3 regular graphs. And any eigenvalue that's in this region will have an almost linear number of nodal domains. 3, yes.
And the top eigenvalues are expected.
Yes. Yeah, the top eigenvalue should have a small number of nodal domains, but this only gives information, yeah, in this region. Here we still don't know anything. And yes, the result becomes weaker the larger that D becomes.
I'm sorry, so wait,
Yeah.
anything about like the top eigenvalues?
No, except for that they're, the Davies et al. Result, which says that the kth eigenvector has at most k. There's no non-trivial lower bound. Like we don't know that there are more than 2. Yeah. Yes.
Question, so for the highest eigenvalues, like I know we have this other paper about like the number of eigenvalues that are close to the second eigenvalue. Could that be one of the reasons why for the highest eigenvalues are those 2 because they're like very similar to the second eigenvalue?
Yeah, I think that's a good way to think about it. The way that I usually think about it is that if we believe that random regular graph eigenvectors have this Gaussian behavior, then what we'll see is that the covariance depends on the eigenvalue, right? So if I have a higher eigenvalue, then my covariance is higher, which means that positive entries are closer to positive entries, which means that there will be less nodal domains. Intuitively, that's the what's going on here. Okay, so yeah, like I said, this result gets weaker the larger that D is, right? So this is for a 40 regular graph, right? And once again, this is the Kessler-McKay measure for a 40 regular graph. And it's only for this small fraction of the spectrum that our result actually holds. Yeah, that's usually what happens, right? But yeah, the issue is really just this -2 square root D minus 2. And yeah, I'll get to why that's the bound that we get, but yeah, it is annoying. Yeah, I mean, a weaker version of the result that they prove is if I take a graph and then any equal partition that I have into n over 2 vertices splits almost every eigenvector into equal mass. Right, that's a weaker version of the result that Anand Paraman and Laplacian proved. Okay, so, but yeah, we're still happy though, because this is the first result lower bounding the number of nodal domains for random regular graphs. It should be noted that some of our results were for the adjacency matrix, some for the Laplacian, but for regular graphs, these are the same. So you could equivalently say for the high energy eigenvectors of the Laplacian. Okay, so how do we actually show this? What we prove is that the number of singleton nodal domains of one vertex is omega n over polylog n. So that's the only thing that we end up counting. Yeah.
Because we were talking about like eigenvalues of the Laplacian.
Yes.
Now, like this result is with you need like something about the eigenvalues of the adjacent matrix.
Yes.
Talk about nodal domains of the adjacent matrix or the Laplacian matrix.
Oh, so these have the same eigenvectors because for the Laplacian is just D minus the adjacency matrix. For a regular graph, that's just a multiple of the identity, right? So the high energy eigenvectors of the Laplacian are just the most negative eigenvectors of the adjacency matrix. But yeah, that's worth clarifying. Okay. So we show that the number of singleton nodal domains is omega n over polylog n. So a singleton nodal domain is just a nodal domain of one vertex. So something that looks like the left, right? Where a vertex is positive and it's surrounded by all negative entries versus something on the right. Okay. So what behavior should we expect? So the covariance in Berry's conjecture, once again, was this function of, this Bessel function. But the important thing is that, or the thing to highlight here is that as the distance between two points gets further and further, the covariance approaches zero. It converges to zero. So an analogous statement of graphs would mean that entries behave in a Gaussian manner, and the covariance should depend on the distance between two vertices. So almost everywhere, a random regular graph will look like a tree. So if I look at almost every local neighborhood in a random regular graph, it's tree-like. So first, we can try to understand what this covariance should look like in the infinite tree. Okay. So this result of Elon from 2009 says that there's actually a unique joint Gaussian distribution on the infinite tree, such that every entry has unit variance. The distribution is automorphism invariant, and it satisfies the eigenvector equation at each vertex. And this is what he dubbed the Gaussian wave. Okay, so just to see what's going on here, now I'm looking at the infinite tree. I then put a Gaussian on each vertex of the infinite tree. And what I want is that this joint distribution of Gaussians should satisfy the eigenvector equation at every single vertex. So just as a warm-up, let's talk about what the covariance should be of two neighboring entries. So here I just have the eigenvector equation. So I multiply both sides of the eigenvector equation by x0, right? Then I take the expectation on both sides. Then I use property 1 and property 2. So what I know is that the expectation of x origin squared is just 1. So this just reduces to lambda. And what I said is that there's automorphism invariance. So this product, the expectation of xo times each one of its neighbors is the same. So I just get d times the expectation of one of these. So what that gives us is that the covariance of two neighboring entries in the Gaussian wave should be lambda over d. So this can be extrapolated out to vertices of farther and farther distance, right? But there's this fixed Gaussian wave structure. Okay, so if Berry's conjecture were going to be true in the discrete setting, then covariances should be those of the Gaussian wave. So 2 years ago, Backhouse and Segedy prove a version of this, which is, yeah, a very nice proof that I'll try to explain the result now. Okay, so what they show is that you can think about it as the following is the case. If I take an eigenvector of my graph, And then I sample a vertex of my graph uniformly at random. I then look at the neighborhood, the R, so for some fixed R, the R neighborhood of that vertex, right? So that induces, if I just think about uniform sampling over my graph, that induces a distribution of R neighborhoods, which therefore induces a distribution in RD if I look at the eigenvector on those neighborhoods. And what they show is that this distribution converges to the Gaussian distribution, specifically that of the Gaussian waves. So what I'm saying is I have two things here. On the left, I have a graph. On the right, I have the infinite tree. What we said is that locally, usually it will look like a tree. So what I do is that I randomly sample a vertex to be my central vertex. And then, for example, if R equals 1, I just look at the value of the eigenvector on that vertex and the value on all of its neighbors. What the Backhaus-Segedie result says is that that distribution, which is induced by just sampling this vertex at random over the graph, is very close to the distribution, the joint Gaussian distribution of the Gaussian wave that I just gave you, which is just given by, I have 4 Gaussians with the given covariance from before, and I just sample them at random. So these two distributions are close to each other. The thing that we should note, though, is that I have this parameter sigma, right? And this is just, it approaches the Gaussian distribution for some fixed sigma in 0 to 1. Okay, well, this is good news. Because if I have a negative eigenvalue, then these entries, an entry and its neighbor, are going to be negatively correlated in the Gaussian waves. So that means that with some constant probability, I'm going to have a singleton nodal domain. The only downside is that we don't know the variance of the Gaussian that we're approaching in this Backhaus-Segedie result. And the variance could even be 0. So in this case, the eigenvector distribution's proximity to the Gaussian wave doesn't imply that there are many singleton nodal domains. The other thing that this implies, though, is that our eigenvector is localized. So what we're saying is that if you think about the entries of the eigenvector converging to a Gaussian, so if this Gaussian has non-zero variance, then the proximity to the Gaussian wave will imply that there are many nodal domains. But if this Gaussian is 0 variance, then there's no such implication. But we get some added information. We now know that our vector is localized, namely that most of entries of our eigenvector are very close to 0. So just to really make it clear, if I have a delocalized vector, so sorry if you can't read this, but I have entries in each of these. The point is that if my entries are large and if I perturb it, I can't change the sign of my entries, so I keep a nodal domain, whereas if my entries are small, then a perturbation can change the sign, which is bad, because I destroy the nodal domain. Okay. So what we said before is that we're close to a Gaussian, right? So we're close to the Gaussian distribution, right? So if I'm close to a Gaussian distribution of high variance, that means that any perturbation just means being close to, basically going from a Gaussian to going to what my empirical distribution is, right? So if it's high variance, then it's fine. If it's low variance, then just being close to this Gaussian distribution doesn't actually imply that there are a lot of nodal domains.
We didn't see that the width of the Gaussian from the previous slide would be relevant to this.
Okay.
I don't know. I mean, if every node is picked according to a Gaussian, right?
Yeah.
The same Gaussian. And then you partition them according to sign.
Well, think about let's say that I'm close to a Gaussian of variance 0. That means that all of my entries are 0, right?
Closer.
Yeah.
Oh, okay. But the limit of 0 is not really useful. If anything except 0, it's gonna
But what Russ said is you're talking about some kind of deviation of a fixed amount.
Right,
Yeah.
the thing, like you're gonna be close, so like each entry might be off from the Gaussian by some amount, and then this is like this, that those arrows is off.
Yeah.
And that change what you want to get from the Gaussian. Like you look at the Gaussian, that was fine.
So there's part of the issue that we don't, the result doesn't say what that sigma is.
Yeah, it doesn't say what the sigma is. So we have no control over that. So this solves the question if sigma is not zero, right? But if sigma is zero, then we know that our eigenvector is localized, but it does not solve the question. Any other questions? Okay. So, all right. So what we need to do now is solve the problem if the Gaussian that we're close to has variance 0, right? Which is equivalent of saying solve the problem if our eigenvector is localized. So what we'll use is another connection between the infinite tree and the random regular graph, which says that the entries of the Green's function of a randomly selected regular graph approximate the entries of the Green's function of an infinite tree. So we want to use the Green's function to analyze the structure of one eigenvector. However, because this result only holds when the imaginary part of the Green's function is at least log to Cn over n, we cannot separate an eigenvector from its closest log Cn neighbors. So what we're saying is that we're taking, so yeah, sorry, once again, this is a result. And what we're doing is that we're taking a Green's function and we're trying to localize it on one eigenvector to get information about that eigenvector. So what we want to do is get this number z as close as we can to that individual eigenvector. So the average distance between eigenvalues is 1 over n. This Green's function to focus on one eigenvector, we should have the imaginary part be theta 1 over n. However, if the imaginary part of z is greater than or equal to log to the Cn over n for some constant c, then we cannot separate the desired eigenspace from the closest log to the Cn eigenspaces. So nevertheless, this does give us a lot of information about our eigenvector. Namely, it implies a nearly optimal bound on the infinity norm of the eigenvector. So this is a series of work of Roland Bauer-Schmidt, Jiayang Huang, and H.T. Yao. And then Huang and Yao had a follow-up work. And one of the things that this Green's function bound implies is that the infinity norm of an eigenvector is at most polylog n over square root n. Okay, so that doesn't quite get us all of the way there. So I'll present a simpler version of the ideas that we end up using to get us from that result to the nodal domain result. And how much time do I have? 10 minutes? Okay. So let's assume that we have an eigenvector of very, very small eigenvalue. So now we have value minus d plus 1 minus some small epsilon. No, so this is a simplified version of what we actually end up doing. Yeah. It will exist for d equals 3 or 4, for what it's worth. So consider a vertex that is not a singleton nodal domain and such that it has a non-negligible amount of mass in the eigenvector. So let's look at the eigenvector equation, right? So what we get is that we assume that it's not a singleton nodal domain. So what that means is that it has some neighbor that is of the same sign. So another way of saying that is that it has at most d minus 1 neighbors that are of the opposite sign. And the only way for this to happen, remember that lambda is less than minus d plus 1 minus epsilon, is that there must be some neighbor which has larger modulus in the eigenvector. That's the only way that can happen. Okay, well then let's iterate this process, right? So if this new vertex that we're at isn't a singleton nodal domain, then we can find an even larger vertex. And we just keep on doing this. And if we have an infinity norm bounds, like the one that I just gave you, then we can only iterate this process c times log n times. So sometime in that sequence, we must have reached a singleton nodal domain. Moreover, by the delocalization result, we chose a starting vertex, right, which had a non-negligible amount of mass. So by delocalization, there must be many such vertices that we could have started from. Meaning that in total, many vertices are close to singleton nodal domains. Okay. But as Ryan mentioned, this doesn't really help, right? Because the eigenvalue is too small. So this doesn't give anything when d is greater than or equal to 5. Just because of the spectral radius of a random regular graph outside of the trivial eigenvector about. Okay, so to achieve a better bound than what we just did, we have to work globally. We can't do this local analysis. Okay, so we start in the same way. Let's start with all of the vertices such that the value in the eigenvector is non-negligible. So assume that none of these vertices are singleton nodal domains, none of them. Then, similar to what we did before, there must be some neighbor of the same sign. So that means that we can remove an edge bordering that vertex while only decreasing the Rayleigh quotient. So what I'm saying is that if I have something, this is the Rayleigh quotient. So if what I start from is something that looks like the left, then all terms corresponding to u in the Rayleigh quotient are negative, right? But however, if it's not a singleton nodal domain, then there's at least one term that's positive. And this is an edge that can be deleted. Okay, so what do we do? So what we do is that we actually localize onto the set of vertices that contain the majority of the L2 mass. So what we said is that we can assume that our eigenvector is localized. So we do this. If there are a few vertices that are singleton nodal domains, then we further localize onto vertices that are not singleton nodal domains. So let's assume that the result is not true. We then delete all edges that are positive in the Rayleigh quotient. Once again, this can obviously decrease the Rayleigh quotient. Okay, so as there are no singleton nodal domains, we have deleted at least one edge from every vertex that remains. We're left with a subgraph of maximum degree d minus 1. And the new Rayleigh quotient on the subgraph is it's smaller than the original Rayleigh quotient plus some small number epsilon. It's almost as small as the original Rayleigh quotient. So once again, what we're doing is that we take our original graph. Let's say that I'm then localized on some set of vertices in the eigenvector. I then look at the induced subgraph on that set of vertices. Okay, I then divide those into positive and negative vertices. Now, if any of these edges go between two vertices of the same sign, I can delete them again. So at no step do we significantly increase the Rayleigh quotient. Therefore, the new Rayleigh quotient is less than or equal to lambda plus some small epsilon. So this subgraph is small, and it has maximum degree d minus 1, but still it has approximately the same Rayleigh quotient. So yes. So yeah, let me just explain this. Yeah, I'm almost done. So once again, random regular graphs, they locally look like trees. Remember that we localized to a small set, right? So what that means is that whatever set that we localize on should look tree-like. Trees, we can bound the spectral radius of, right? And specifically, we can bound it in terms of the maximal degree of the tree. Okay, so what I claim is that because the maximum degree is d minus 1 and the graph is close to tree-like, the spectral radius actually can't be that much bigger than 2 square root d minus 2 when I have passed this induced subgraph. Okay, so I won't have time to show this, but what we show is that for subgraphs that look like the subgraph, for graphs that look like the subgraphs of random regular graphs, the quadratic form on this tree-like graph is a convex combination of the quadratic forms of a small multiple times the spanning trees on the subtrees of this graph. Okay, so the resulting graph is close to tree-like, has maximum degree d minus 1. Therefore, the spectral radius is at most 2 square root d minus 2 plus epsilon. That means that the lambda that we started out with has to be greater than or equal to minus 2 square root d minus 2 minus epsilon. I think I said 1 before, I meant to. Okay, so if lambda is less than this, then our assumption that there are a few nodal domains must have been false. All right, so I know I'm pretty much out of time. So let me just highlight one. The obvious question is doing this for other lambda, but also another thing is Ronan Eldon, Han Huang, and Rudelson talk about, so we have the sparsity, right? So can we do this for Erdős-Rényi graphs that are close to the connectivity threshold? So very sparse Erdős-Rényi graphs. So they propose looking at this problem, and that's something that's open as well. So yeah, why don't I just stop there? Thanks. Oh yes, so Leo considered initially you want to do this for the random non-regular graph, for the Erdős-Rényi graph, but it ended up, the structure ended up being trivial. But the actual geometry of nodal domains, so classifying vertices by their distance, their size, stuff like that. G1/2, it's just two nodal domains that are the exact same size. Every vertex borders the opposite nodal domain. Yeah. Sorry? Yeah, so that was the first result. That ended up being improved to just 2. And that's true for GNP, for p greater than or equal to. They proved it for like n to the minus 1 over 20. But I imagine it's true for any polynomial. Yeah. Yeah. Yes. Yeah, still open for these, yeah, like quantum billiards. And yeah, I guess the regular graph equivalent, at least in the random setting, would be, could you show that that the variance of the Gaussian that you're converging to is non-trivial, right? That would be a very nice result and would show this random behavior.
So your proof is like 2 parts, right? We don't know what the sigma is. If sigma is large enough, then we have a simpler proof. If sigma is small, then we have.
Yeah, we have to do this local analysis. Yeah, exactly.
know that you can construct like, can construct like regular graphs or like lots of like localized aspects. How is it? For like random graphs, the most eigenvectors are not being localized. Is that
Well, we don't know is the thing, right? So there are a few things we do know. We know that one result is if it's delocalized, then it's Gaussian, right? If it's localized, we have this infinity norm bound, which sorry, I kind of rushed through, but this result of Jiayang Huang and HCI, which says that the infinity norm is bounded. But the problem is that we don't know whether it could be just that like, so it's polylog n over square root n. We don't know whether it's just that on n over polylog n entries and 0 everywhere else. That's the bad situation, I guess, that we have now.
Are you from this area?
Uh,
Where are you from?
I'm from New York.
From New York.
Yes. I'm visiting from Berkeley. I'm originally from New York, which might explain why I said Courant, that might be a New York thing.
Are you also visiting other places on this trip, or you just flew out to the talk, or?
Yeah, I'm just here for the week, hanging out with Prasad. Yeah.
Sorry, I did it first. No. Yeah, but I want to go out. I appreciate it.